Good afternoon. Can everybody hear me? I'm loud and clear? Good. So this is not a security talk, but this is a talk that involves verification. And particularly I want to talk about verifying distributed systems for concurrent separation logic. This is a project that's led by Upamanu Sharma, who's a PhD student at MIT, and it's joint work with Ralph and Joe, who are at ETH and NYU, and with Nikolai Zaldovich, who is at MIT. So let me see if this actually works. Top end, good. So distributed systems, as you probably well know, power the cloud. They aggregate a large number of machines in convenient abstractions for application developers. So think, for example, Amazon offers S3, a storage system that's a key value server, even though it's running on a large number of distributed computers. Think about Kubernetes, Google's Kubernetes, and a way of arranging computation on the cloud. Or Cosmos DB, Microsoft's offering for writing cloud applications using databases that they offer. And it turns out that kind of software is actually very complex because the code, even though it offers us a nice abstraction to the application developer, the internal code actually is complex. It has to deal with network failures. Packets can get lost. It must handle concurrency between nodes and within a node. It must recover from crashes because there are many, many machines. Some of the machines might actually fail. And because machines fail, the data needs to be replicated so that it's always available if one of them replicas fails. It must provide high performance. It must be able to reconfigure. Like if a machine is permanently failed, we need to be able to replace it. And this all might be going on at the same time. So we might have a reconfiguration going on while replication is happening, and concurrency is going on. And so it turns out, it's actually hard to get this kind of software correct. There's basically complex protocols that interact in different ways, and if you sort of think about it from the developer's perspective, basically the developer has to consider many possible executions or many possible interleavings and reason about all of them. And it's very difficult to test for those. And so in practice, people actually make bugs. And so there's quite a number of bugs in these digital systems. And often, of course, they don't really appear as anything serious. Maybe you see a short, timeout or a short period of time where, for example, you can't download your Spotify song, but like a couple of minutes later, it's actually all up and running again because the machines and the distributed system configured correctly again. However, once in a while, the bugs can actually be catastrophic. And for example, Amazon has this bug where in 2011, where basically the whole East Coast data centers were down for many, many, many hours, and many websites actually couldn't deliver any service at all. And this is not restricted to Amazon. Google had something similar in 2019, where the machines, was a bug, and as a result, many websites, including Google's own internal services like Gmail, were actually not working. And what is interesting is that actually people do publish the root cause analysis of actually why this happens. And of course, with these kinds of really catastrophic bugs, there's many things that sort of interplay together. But in all of them, there's actually sort of a key, critical bug that actually showed up that never showed up before. So for example, in the Amazon case, there was a race condition in the code on the elastic block servers nodes that just only happened occasionally, and then they were shut down themselves, making the situation even more worse because people wanted, other nodes wanted to have to copy yet for the overload to get other nodes. So it would be nice to not have these bugs. And as I already said, clearly companies spend a lot of time and energy to testing them, and nevertheless, they happen. So recently, in the last decade, researchers in distributed systems have returned to an old idea that Adam already talked about, namely verification. And in this approach, in addition to writing code, you write a specification that tells like how the system is supposed to behave. You use a proof assistant, and then you prove with the proof assistant whether the code actually implements the specification. And if you get a correct proof out of that, then you get this nice benefit that basically it excludes large class of bugs. It just cannot happen anymore because you prove that they're not there anymore. So this seems a super promising approach. And because of the underlying technology, the verification technology has so much improved in the last couple of decades, it actually starts becoming feasible to think about this actually for realistic systems. So there have been in the last couple of years some recent successes in distributed systems trying to verify pieces of this puzzle. So for example, there's work on concurrency, there's work on crash recovery, there's research progress on replication, there's research progress on reconfiguration. And what I want to do in this talk is actually tell you about a way of doing it that actually does all of these at the same time, and also argue reasons about the interactions between them. And this basically enables you to actually build or verify realistic sort of distributed systems. So to give you, I need a sort of example to be able to illustrate actually how all this stuff works. And so I'm going to take a very simple example, a key value store, which is a popular cloud abstraction that is used by application programmers to store data. And the abstraction is very simple. It maps a key to a value. So you might have a key is like building 45, and then the description might be the value, the Schwarzman College of Computing. The other thing that's nice about this particular key value store is that they often have a very simple spec, where the specification is often captured by the notion of linearizability. And with linearizability, what it really means, or in essence what it means, is that even if the key value store is implemented as a distributed system running many nodes, things happening concurrently, crashes, whatever, reconfiguration, the linearizability says that the system as a whole basically behaves as a single machine key value store. And so you do a put, and if you do then a get, you get the result from the last put. Now, implementing such a key value store with linearizability is actually tricky. And so to make it a little bit more clear, typically, in a system like this, when the client does a put, the key needs to be replicated and the value needs to be replicated to multiple nodes just in case one of them fails. And that involves some replication protocol. Now, of course, one of those replicas may be permanently damaged and so needs to be replaced. And so typically, a system like this also has a reconfiguration server, which basically initiates the changing of replicas. And of course, it's a little bit tricky because once, if you copy the data from one replica to another replica and then pursue and continue, you got to make sure that basically you lose no puts. You might make sure that you copy from the last node that actually has all the latest puts in it. Otherwise, you might lose one. So it's a little bit tricky. But typically there's more tricky, but we want to get high performance. And if you look at this get actually is reasonable, or the put is actually reasonably expensive because it involves multiple nodes. You got to talk to the primary, then to the backups. The primary has to wait for the backups, and the backups respond to the primary, and the primary responds to the client. And it's sort of too bad. You got 3 replicas. Why couldn't you get much higher performance? Right? And so typically, people have a trick called Leases, which I will say a lot more about, that allows actually a client to talk to one replica and then actually return the result if the lease is still valid. And so all these 3 things actually do interact with each other. The replication protocol interacts with the leases interact with the reconfiguration, et cetera, et cetera. So our goal in this work, or this sort of line of research, is to prove a top-level theorem of the form, all the puts and gets you do on this key value store are linearizable in the presence of reconfiguration, concurrency, network unreliability, crashes, et cetera, et cetera. So you think about this for a second. This theorem is extremely powerful, right? It takes care of protocol bugs, it takes care of implementation bugs, it takes care of off by one errors. These are wide classes of set of bugs that are basically eliminated by this theorem. Now, of course, there's a little bit of a challenge here. You got to prove this theorem. And the reason that it's complicated is in the proof, you don't want to prove that basically says well, I'm going to consider all possible executions, work for every execution, and then prove that actually the theorem holds. That would be a painful way of proving the theorem, because we don't really want to enumerate them explicitly. So we're looking for some proof approach that basically allows us to talk about all the possible executions without actually having to explicitly enumerate them. And it turns out there's a great idea came out in 2007, which is called concurrent separation logic, which allows us to, helps us achieving this particular goal. And concurrent separation logic is a logic, like any other logic. So it has a set of inference rules, modus potens, except, this particular logic is designed in a very, very careful way to allow for very modular reasoning. And what that means is that we can reason about one thread of execution without actually having to consider all the other threads of execution. And this is basically almost like reasoning about a sequential program, where you can write a sequential program for a while without having to consider any other program. And so this hopefully gives us a stepping stone for achieving this idea of not having to enumerate all possible executions. So our main extension is actually to take basic concurrent separation logic and extend it to distributed systems. Consider separation logic, as the name indicates, was designed for basically a single machine with multiple threads, multiple cores that run concurrently, and then reason about that concurrent code. And so what we've done is basically extend this to having a notion of machines, with machines having multiple threads, having a network where packets can actually rely, the machines actually can crash, and basically have theorems that allow you to reason about reconfiguration, RPCs, crashes, leases, et cetera, et cetera. And I'm going to give you a little bit of flavor, a tiny, tiny little bit of flavor of this logic and these extensions to get you some sense of what kind of research this is. The key goal here is that actually using Grove, we actually can build and then verify pretty realistic distributed systems. So I'll come back at the end of the talk. So I'm going to tell you a little bit about concurrent separation logic, just to give you a flavor, and I need to present that because before to be able to explain our extensions to it. So let's say you have a simple program that's run as a single thread which manipulates a variable x. Concurrent separation logic gives you an assertion about logical resources. And logical resources are basically proof concepts that, for example, correspond to this particular physical variable x. And in these assertions, the particular assertion that's really important in concurrent separation logic is this points to relationship, which says two things. It actually says what the value that's associated with this variable x, but it also gives the holder of the current thread exclusive ownership to that particular resource. And so this is nice because we have another thread that can not even manipulate this variable x because it can't get exclusive ownership to it. So we don't even have to consider all the other threads of execution in this particular program. We can just reason through this, sequentially through this program, this particular thread, and update the proof state to correspond to whatever the physical program is actually doing. So that's sort of this ownership is a very, very powerful idea that allows for this modular reasoning. Now, of course, we do want to share, occasionally. And so the second thing is that the concurrent separation logic allows you to actually share. And the way it goes is actually through invariants. And these are things that have to hold between every atomic step of execution or outside of a lock or outside of a critical section. So for example, in this particular program where we have a lock, that that protects the variable y. That would be a typical way of writing a concurrent program, then put a lock at the end. With that lock is associated on a lock invariant. And the lock invariant is closed, but at the point that the thread that actually acquires the locks exclusively, at this point it has exclusive ownership of the lock, it is allowed, the logic allows the proof to open this particular resource or this particular invariant and actually grab, basically the points to out of the lock invariant, manipulate it for a little while, and at the point of the unlock, it actually has to close it up again and put it back into the lock invariant. And so the logic is set up, that it has inference rules that basically allow you to open invariants, close invariants, take ownership of a resource that sits in a lock invariant so that you can, use it to share state between different threads of computation. So this is a wonderful property because even in this particular scenario, while we're reasoning about this thread on the left, we didn't even consider the thread on the right, right? And so again, we sort of keep our sort of goal of having this strict separation. And there's no wonder it's called separation logic. So all these resources I talked so far about, x and y, are basically physical resources. And of course, it's convenient in a program to actually also be able to talk more of abstract resources, like resources that describe the state of the system at a high level. And particularly in the proof, that's going to be important. And particularly in distributed systems, there might be high-level properties that be true about the system. That's not true for any particular node in the system, but just only at the abstract level they're true. So for example, one of those properties that you may want to cover is the current configuration in the distributed system, where if you think about the distributed system moving through epochs, that's a common way to think about it. You start at epoch 0, then epoch 1, epoch 2, and at each epoch there's some number of nodes that are part of that particular epoch. And this is important for reconfiguration. So one thing that is convenient to have is basically some abstract notion of what the current epoch is. And so in concurrent separation logic, you can just have, in the proof, you can sort of declare an abstract state, an abstract variable that actually also has points to's. And so the same points to that apply to physical resources can actually be applied to these abstract resources. And so, of course, there's only one piece of execution that can actually own the points to ownership. And it's often convenient in a distributed system to also have a sort of second type of assertion that basically expresses the knowledge of a particular resource. So for example, this expresses that the current epoch is at least E. So this gives you a lower bound on the epoch number. Since the epoch numbers are always increasing, you might have learned that, for example, we're at least at epoch 2, and that's always valid. And so, for example, the holder of the points 2 can update the epoch number, but your lower bound is still valid. So this is convenient to reason in distributed systems, for example, in the context of the configuration server. The current configuration server, of course, is probably the owner of the current epoch, because that's the one that actually decides who is a new configuration is going to happen, and it can actually update it. But for the configuration server to actually make a decision to go to the next epoch, it needs to know that every replica, or at least the proof, has to establish that every replica actually is at least has seen epoch, is past epoch E, or is at epoch E. And so that means, for example, in this last case, for the last replica, in the proof, we have to demonstrate that E old is at least E, to be able to move to the next epoch. And this is exactly what the configuration server needs to do in the proof. And so these pieces of these lower bounds are very helpful to reason about in the proof about actually how to move forward the system from the next one epoch to the next sector. Okay, so far, that is just concurrent separation logic. I told you really nothing new, with small extensions in the sense that we reason about threads within a machine and not just threads within threads on different processors or on different machines and not just threads within a single machine. But now I want to show you some extensions that allow us to talk about these interactions between different pieces. And I want to talk about two interactions. One interaction between reconfiguration and the interaction between leases. And give you a little bit of a flavor of how you can reason about it. And remember, the key thing that we needed to prove, correct, is that when the client responds to when the replica responds to the get of the client, that actually no new configuration is started, and that the replica has the latest version of the key value store. So basically the way this happens, or people do this in distributed systems without any proving at all, is just using leases. And a lease is basically a statement that says something is true for the next couple seconds. So for example, the configuration servers might promise that when it gives a lease to a particular replica, I'll promise you I won't change the configuration for the next second. And this allows the replica to make all kinds of decisions without actually having to talk back to the configuration servers. This requires, of course, that all the clocks in the distributed system are actually synchronized. And people have designed a system to actually do so, and you basically leverage the model of synchronized clocks that Spanner introduced in one of a Google system, which basically says we know what the time is with some error bound. So now I want to sort of talk about how do you use leases in the distributed key value store as you write normal code. So the replica presumably goes to the configuration servers, asks for a lease, gets a lease back saying the configuration is valid for the next second. If a get comes in, the replica can basically look at the current time, compare the current time with the expiration time of the lease. If the expiration time, or if the current time is before the lease's expiration time, it's totally fine to actually look up the map. Then the replica knows it has the latest information, looks up the key in the map, returns the result to the client. And of course, what is cool here, correct, which I didn't really show here, is that this replica didn't have to talk to anybody to make this decision. Right? So you just go ahead and do it, which allows us to get much, much higher performance than, say, for the puts, where the puts actually have to talk to multiple machines. How do you change from one configuration server to one configuration to the next one? Well, at some point maybe a client notices that actually a machine is permanently damaged, tells the configuration server, please, enter a new epoch. The configuration server basically waits for a second until all the leases have expired, and at the point that all the leases have expired, then it says, okay, here's a new epoch. And of course, in the proof, we need to demonstrate that at this particular point in time, when it actually returns a new epoch, to the client, that there are actually indeed no more leases. So how do we do this? So one idea that Grove has is we introduced this idea of a time-bounded invariant. And they look a lot like our lock invariants, except there's a time associated with them. So this notion, this informal notion that basically no reconfiguration is in 1 second, we capture by a new, if you will, a new invariant, which we call indeed, the time-bounded invariant. And basically the time-bounded invariant has, like the lock invariant, points to inside of it, then it's closed, and so only in particular cases can you open it. And furthermore, that time-bounded invariant is actually locked by the lease, or closed by the lease. And the lease actually has an expiration time, and that will allow us to reason about expiration time. And it turns out for convenience, it's also nice to actually have this lower bound, that's shown here before, as before for the current epoch. The logic, the logic extensions that we made, to the concurrent separation logic and to Grove is to actually have a set of rules that go along with this time-bound invariant. You can access it, there's a creation rule, there's an expire rule, et cetera, et cetera. So a bunch of new inference rules to actually allow you to actually reason about these time-bound invariants and use them in your proof in a way that is completely sound. So give you a little bit of flavor of like how the proof would go. Let's consider the replica. The replica, we're going to consider the get first, and then we'll talk about the configuration servers. But the configuration server is actually the one that actually creates these time-bounded invariants. It owns the L points to t, and actually it can create a time-bounded invariant. So the replica, and so what does this time-bounded invariant say? Well, for the time of the lease, the time-bound invariant is valid, and at some point it expires, and then it becomes invalid. So I'm going to ignore the configuration server for a second and just talk about the replica. Well, the replica gets a lease from the configuration servers in the code. And if the code gets that lease, then we can conclude that the lower bound is at least past the expiration time. So the lease is past the, not past the expiration time. So when a get comes in, we can take that particular fact and combine it with the current time. And if the current time is below t and the lease is valid at least past t, then the rule for access allows us to open the time-bounded invariant for one step in the execution. We can extract the points to out of the time-bounded invariant, look at it and say, well, this is a valid epoch because it points to E, we're in the latest epoch E, and therefore our replica is completely up to date and no new epochs have started, and so therefore we can actually respond to this request. And then the rule basically wraps up the points to back before the next step of execution back into the time-bound invariant. So this gives us a sort of a sketch of the proof. We prove using these time-bound invariants that a replica actually is up to date, assuming that the code is written correctly. So let's look at the configuration servers. And in fact, one of the things that I should point out here is, of course, while reasoning about this replica, we didn't really talk about the configuration servers at all. We were able to reason about it without actually considering it. Now let's consider the configuration servers. The configuration servers actually owns that particular L points to t, the expiration time, which allows it to basically build these time-bounded invariants and put them in the current epoch into the time-bounded invariant. And at some point, the client, correct as before, the client asks, please enter a new epoch. The code will wait for a particular period of time. We'll look at the current time, and if the current time is past t, we have an expiration rule that combines the ownership of the lease that allows the owner of the lease to actually open the current epoch, but the current epoch, the time-bound invariant, because the time-bound invariant has expired at this particular point in time, because t, actually the current time is bigger than t. The two combined allows the current configuration server basically to get permanently back, this owns to, or this owns to points to, and allowing it basically to update it. So it updates it, and then increases it, can put it back into the time-bounded invariant for subsequent epochs, and return to the client that actually the configuration has changed. And the configuration can do this because the logic basically proves there's no other option. The logic proves that basically the lease has expired and that nobody else could have updated the current epoch, because the only one that can actually can update the current epoch is the holder of actually the lease itself. So that gives you a little bit of flavor of like the kind of reasoning that you can do using this extension for concurrent separation logic. And again, really the main takeaway actually of this exercise is to demonstrate, correct, that we're reasoning about the configuration service, again, independent of the replicas itself. So we can talk about the replication protocol completely independent of actually the configuration service, but still capture the key interactions between them, using this, for example, this notion of time-bound invariants. And so the Grove library has a whole bunch of other, sort of primitives, like these, to be able to sort of reason about realistic distributed systems. And in fact, we built a distributed system in Go. It has a lot of different components. It has replication protocols. It has different types of replication protocols, like primary backup, Paxos-based replication protocols, for example, to replicate the configuration servers. It has a verified key value store. It has a little support for transactions. And so it basically has all the key ingredients of a real sort of distributed system, like the hard aspects of a distributed system. But it's not a real distributed system in the sense that the implementation is actually very small. It's 3,000 lines of code. And if you look at real-world distributed systems, they're much, much, much larger because they implement all kinds of other features. But we believe that this particular prototype sort of demonstrates all the key features that actually show up in real-world distributed systems. The proof overhead, for proving these 3,000 lines of code is about a factor 10. And that includes writing all the specifications, including the top-level specification and all the intermediate specifications. And you might say, well, 10, oh man, that's a disaster. Of course, we'd like to be lower. But really what the key point of this exercise is that it turns out that previous systems already had a factor 10 overhead. If you're reasoning about concurrency alone, there's a factor 10 proof overhead, and typically for many systems. And we didn't make it worse, by sort of set of extensions, because we can reason about independent pieces. We maintain basically the same proof or overhead as before. And there's a lot of research, as you can imagine, going on trying to reduce the proof overhead in general. And we should be able to leverage that research if those results actually materialize. So that's on the proving side, to just demonstrate to you that actually it's worth having leases. Like I'm going to give you a tidbit of one experiment, so to give you a little bit of a sense that actually matters. So the particular experiment that I'm going to describe to you is a configuration with two replicas. What we're going to do during the experiment, we're going to crash one of the replicas, replica A. We can switch to two new replicas, C and D, so all the data needs to be copied from B to C and D. And while doing that, we're running 32 clients doing gets and 64 clients doing writes. And we just want to see actually what happens. So the first thing, so on the x-axis is time, on y-axis is throughput. On the blue line is read throughput, and the red line is write throughput. And unsurprisingly, the read performance is really good. And this is because of leases, right? Instead of having to, the puts have to go to 3 replicas, or in this case 2, and the reads, you can read from any of the 2 replicas and basically get the result back. And so the throughput for reads is way, way better, for gets is way better than for writes, which is what we hoped for having leases. So this shows that leases actually are important. At around 20 seconds, we kill the primary, so replica A. And it takes a second for all the leases to expire, and then it takes a couple seconds to 25 to actually for the system to reconfigure. One thing that's interesting that is during the reconfiguring itself, the system is still able to handle some reads. Namely, reads that are not dependent on keys that were just written to can actually just proceed. Of course, reads that are blocked on writes, that are blocked on being able to talk to the replicas cannot proceed. But some of the reads can actually proceed, which is very nice. But once the reconfiguration is done, then we enter the new configuration, the new epoch member, and basically the read and write performance go back to what it actually originally was. Right? So this demonstrates, one, the system actually works. And of course, you already should have believed in that because I've given you proof that actually the system, or I've proven that the system is correct, but this sort of illustrates that maybe in a more sort of practical manner. Okay, so with that, I want to wrap up and draw some high-level conclusions. the first thing I think I want you to come away from this talk is that verification has come a long way. It used to be sort of a niche exercise for small programs, and you now have seen two results that are possible with the modern verification technology. Adam talked about crypto libraries, and here you basically see that bug-free distributed systems are in reach. We're not there yet, because they're not as big as the ones that actually, the prototype that I've shown you is not a sort of a real world distributed system, but it does capture all the essential aspects. And so it's certainly possible to actually start verifying more serious distributed systems. Second thing is, when you take away this concurrent separation logic and the extensions to reason about distributed systems really allow you to reason about complex code in a modular fashion. And in the same way you can write programs in a modular fashion, you can now do verification in a modular fashion using this particular logic and this extensions. And so that's a really, really cool result. And then finally, if you're really excited, you can actually download our code and actually start playing with it and build your own distributed systems and verify them using the Grove library that is available at the GitHub. All right, that's all I wanted to say. And if you have any questions, please feel free to ask.